Hi, this is Mrs. Kidman, and in this video, we are going to be discussing how we can graph rational functions that are in forms other than the form y equals a over x minus h plus k. So we've talked about how to graph them in this form, where this a determines our shrink and stretch. So we are going to shrink if a is between 0 and 1. We are going to stretch if a is bigger than 1. And then if our a is positive, we know it's going to be in the quadrants 1 and 3. If it's negative, it's going to be in 2 and 4. Now notice these quotations are because it's in the quadrants created by our asymptotes. Okay, so that's kind of how that a works. Our x minus h here is going to be our vertical asymptote, where x is equal to h, and then our plus k is our horizontal asymptote, where y is equal to k. So we've kind of talked about that before. Now what we want to do is talk about how we can graph rational functions when they're in other forms. So just like we did before, in order to find our vertical asymptote, what we're going to do is we want to set the bottom equal to 0 and solve for x. So whatever's on the bottom, we want to solve for that polynomial on the bottom there. Now that may involve factoring, it may involve algebraic manipulations, but that's what we want to do. In order to find our horizontal asymptote, and now we also have something called a slant asymptote. It depends on the degrees of the polynomials that we have there. So if we are talking about these asymptotes here, if there's the higher degree on the bottom, so we have something like x divided by x squared, x plus 2 divided by x squared plus 4, something like this. Anytime that we have a higher degree on the bottom, that means that our horizontal asymptote is going to be y equals 0. And this is horizontal. And the reason why is we're just going to be straight at that line. Now, if we have a polynomial with the same degree, so we have x plus 4 over x minus 3, something like that, this is also going to be a horizontal slope. But if they have the same degree, then y is going to be the leading coefficient of the first divided by the leading coefficient of the second. So in this case, we've got a 1 and a 1. So ours would be y equals 1 here. If we had a 2 out front, then this would change to a 2. If this was a 7 on the bottom, it would change to a 2/7. You can kind of see how that affects it. But this one is also going to be a horizontal asymptote here. So what this means is when we go to graph it, when we have these horizontal ones, in this case, it would be right at y equals 0. In one like this, we would end up seeing something that comes right here. Now, if we have a higher degree on top, what we're going to end up seeing is we're going to end up seeing what is called a slant asymptote. Now, the way that we find this slant asymptote is we actually want to divide the polynomials by one another. And then whatever the remaining polynomial is, aside from our remainder, is what our degree is going to be. So what we can do here is divide the polynomial, and that will give us our, sometimes we like to call it oblique asymptotes as well, because that kind of depends on the difference there. So if it's a difference of 1, so if we have x squared on top and an x on the bottom, like this, then we would end up getting y equals something that's a line. But if this was an x to the third, then we would get y equals a polynomial sort of look. So it really depends on what we have left over there. But that is going to be an oblique or a slant asymptote. Now, if we have one that's linear, kind of like this example we had earlier, where this was an x squared plus 7 here. If we have something like that, what we're going to end up seeing is we're going to end up getting an asymptote that's slanted here. Now, if we have a slanted asymptote in addition to a vertical asymptote, typically what we end up seeing is that our polynomial is kind of sandwiched in between those two asymptotes there. So it kind of gives us a cool look. So that is our horizontal and our slant asymptotes. It depends on the degree of the polynomial. Now, before we move on to actually graphing these, in which case, after we find those two asymptotes, we're going to use 2 points on either side to kind of decide where our function goes. Before we do that, let's practice figuring out whether we have horizontal or slant asymptotes. So let's first start with this first one. Now, purely depends on the degree. So the degree of this top polynomial is a 2, and the bottom one is a 2. So because they have the same degree, that tells us that we're going to take the leading coefficient divided by the leading coefficient. So this is going to be y equals -3/2. And this is going to be a horizontal asymptote, just so that we are aware there. Now we can take a look at this second one. This one has a degree of 1 up here and a degree of 2. Because it's higher on the bottom, what that means is we are going to have a horizontal asymptote, at y equals 0. Anytime it's bigger on the bottom, it's always going to be y equals 0 for our horizontal asymptote. Now, lastly, we have this one where we have a degree of 2 and a degree of 1. This one means that we are going to have a slant or an oblique asymptote. And what we have to do is divide these polynomials. Now, because I have an x plus 5 on the bottom, I kind of have two options. I can either do synthetic division. So remember, we switch the signs, 6, negative 20, negative 12. We can do our synthetic division here, where we get negative 50 plus 100 or 250. And that ends up leaving us with this 238, negative 238, meaning that our slant asymptote is going to be at the line y equals 6x minus 50. So that's option number 1 of how we find it. So when we graph it, we end up seeing something like this, where we get a 6x minus 50 over here. That's kind of where our slant asymptote is going to be. We can also use polynomial long division to find it. So x plus 5 divided by 6x squared minus 20x minus 12. And we can do our whole process here with our 6x plus 30x. These ones will cancel out. This one changes to a minus. We get our minus 50x. You can see how we're going to result in the same sort of thing. So you can always divide it to figure out where that slant asymptote is, and whatever the remaining polynomial is, that's going to be our slant asymptote. So this just means that we have a slant here. So using these ideas here, what we are going to do is we are going to practice graphing these rational functions. So let's take a look and start with this first one here. Now you're going to see that there's a lot of information up here that we want to fill in. All this information will help us get a more accurate picture of our graph, including things like finding the coordinates of our zeros, our y-intercepts, our horizontal or slant asymptote, vertical asymptote, extra points, domain range. Now the very first thing on here asks us about what is called a hole. Okay, so you may be asking yourself, what is a hole? Well, when it comes to a hole in a function, what we want to do to find that hole is we actually want to simplify our function as much as possible. So in this case, what we want to do is that x minus 2 is as simple as it gets, but we want to factor the bottom here. So we're going to look at factoring two numbers that multiply to negative 6 and add to 1. Well, that's going to be 3 and negative 2. So then we can factor this out as being an x plus 3 times an x minus 2. Now notice how there's an x minus 2 on top and bottom. That right there tells us that we have a hole when x equals 2. Now, the reason why we have this hole is because if I put x equals 2 into this function here, I end up getting 0 divided by 0. Now, you may be wondering what that equals. And we call it a hole because there isn't a specific definition. We actually say that's indeterminate. And indeterminate means that we don't have one answer that makes this true based on the mathematics that we've done. So think of it this way. 0 divided by 0 equals x. Well, 0 equals x times 0. Well, what number can I put in here? Well, I can really put in any number here, right? Because anything times 0 is 0. So because any number works, not one specific answer, we say it's indeterminate and it doesn't work. So when it comes to finding our hole, what we're going to do is take our x value and then find what's left over. So left over here, we've got 1 over x plus 3. And we just substitute that in to figure out the coordinates of our hole. So it's going to be 2, comma, if I put a 2 in here, I get 1 divided by 2 plus 3, or 1/5. Okay, so we would have a hole at 1/5. And what that looks like when we end up graphing it is we just end up putting an open circle there. So let's go back to this problem here. A hole. Well, looking at the top and bottom here, those are both as simplified as they can be, and they don't cancel each other out, so we actually don't have a hole in this problem. Our vertical asymptote, we're going to take our bottom and set it equal to 0, so x equals negative 3. To find our coordinates of our zeros, what we're going to do is we're going to make the numerator of our polynomial equal to 0, so x minus 1 equals 0, meaning that x equals 1, okay, because that is what would happen when we get that. So the coordinate here would be 1, 0, because if I put 1 in here, I'd get a 0 out. To find the coordinate of our y-intercept, we're going to put 0 into our function. So we get 0 minus 1 over 0 plus 3. And we end up getting the point 0, negative 1/3. Fantastic. Now, we need to decide, does this have a horizontal or a slant asymptote? Well, because they're the same, it's going to have a horizontal asymptote, and we're just going to take those numbers in front and divide them. So y is going to be equal to 1, because 1 divided by 1 equals 1, right? Then these extra points. Now, we have these extra points here, 2 on either side of our vertical asymptote, just to help guide us and figure out what our polynomial is going to look like here. So if I put negative 2 in for x, I'm going to end up getting negative 3 out. If I put a 1 in, I get a 0. Negative 4, we get a 5, and negative 7, we get a 2. Now, what we're doing here is we're just doing negative 2 minus 1, sorry. we are doing -2 minus 1 divided by -2 plus 3, and that's how we end up getting -3 over 1, okay? So that's all we're doing is substituting those x values in. So now we have those. Our domain and range is the last piece. So when it comes to our domain and range, our domain is going to be all the real numbers except for the vertical asymptote and the x value of the whole if there is one. So in this case, it's going to be all the real numbers except the number 3. Our range in this case is going to be all the real numbers except for our horizontal asymptote, which is going to be at 1. Now, this is, and if we have a whole, it'll be the y value of the whole. Now, if we end up with a slant asymptote, our domain and range is actually going to vary based on what our graph looks like. And so with that being said, you want to make sure you wait to write that until the very end. So now that we have all this information, let's go ahead and sketch a picture of this graph here. So we've got our vertical asymptote at -3. We've got our horizontal asymptote at 1. We've got our points here that we can plot. And what we're going to end up ultimately seeing is something that looks like this. Okay, so we can use those points to guide it. I can say I have the point -2, -3 right here. I have the point 1, 0 right here. I have the point -4, 5. I have the point -7, 2. Things like that to help guide us and figure out where those go. So that is how we can do it with that example. Now, in this next example here, we are going to look at how we can graph a rational function. In this case, it has a whole, so we want to take that into account there. So to figure out that whole, remember, we are going to factor our polynomial here. So we get x minus 1 over, well, if I factor this using the x method, two numbers that multiply to -2 and add to 1 are going to be 2 and -1. So x minus 1, x plus 2. These are going to cancel. That's where our whole is. So that means we have a whole at the value 1, comma, and then this is really 1 over x plus 2. If I put a 1 in here, I'm going to end up getting a 1/3. So that's where our whole is because I put a 1 in for x here. Our vertical asymptote, we're going to take the denominator of our new function and set it equal to 0. So x plus 2 equals 0, meaning that our vertical asymptote is at x equals -2. Now that's why we want to find the whole first, because we can actually simplify the problem a lot earlier. In this case, we do not have any zeros because our numerator is a constant. The coordinate of our y-intercept is going to be what happens when we put 0 in, so 1 divided by 0 plus 2, and we end up getting the point 0, 1/2. Our horizontal asymptote, because the bottom is actually bigger than the top, what that means is it's automatically going to be y equals 0 based on that pattern here. Now, just like before, we can plug these values back into our polynomial to figure out what it is. And we want to make sure that we plug these extra points into the original polynomial here, okay? We can also do it into the new one. It kind of depends on what you want to do. So let's plug it into either of those. I'm going to plug it into the new one because our numbers then become smaller. So here we've got 1 divided by -1 plus 2, which is 1 divided by 1, or 1. We can follow that same process and we end up getting that -3 produces a -1. If I put 0 in, I get a 0.5 out. And if I put -4 in, I get a -0.5 out. Awesome. Then we're going to have our domain and range. So as mentioned in the previous example, when we have our domain, it's going to be all the real numbers except for our vertical asymptote and the x value of our whole. Our range, in this case, is going to be all the real numbers except for our horizontal asymptote and the y value of our whole. So now when it comes to graphing this, I'm going to kind of scroll down here. What we want to do to graph this is we want to draw our horizontal and vertical asymptotes. So we've got one here at -2. We've got one here at 0. And then what we want to do is plot our points here. So I've got the point -1, 1. I've got the point 0.5. So we know that this is going to look something like this. I've got the point -3, -1. I've got the point -3, -4. So this is going to look something like this. Now our last piece is this whole here. Now at our whole spot 1, 1, 1/3, we want to put an open dot there, just saying that the function doesn't actually exist here, but it comes as close as it can to that point, and then it goes as far away as it can from that point. So that's kind of how we want to figure that out there. Now we are going to take a look at one last example here. So you can see we've had some where the top and bottom are the same. We have some where the bottom is bigger than the top. We're going to take a look at this last example here. This is one where we're going to get one of those slant asymptotes where the top is bigger than the bottom. So let's take a look at this question here. and see what we can do. So very first, before we do anything else with these, the ones where the top and bottom are bigger, we want to check to see if we have a hole. So let's start by trying to factor it. Well, I'm going to try to factor it. What are two numbers that multiply to 6 and add to -4? I don't know about you, but I can't come up with one. So if we can't come up with one, the next thing we want to do is use our discriminant, or that b squared minus 4ac, to decide if there are even any real possibilities. Because if there are real solutions, we want to use them. If there aren't, then we don't. So let's go ahead and figure out, are there any real solutions here? So we're going to do -b, or just b, so -4 squared minus 4 times 1 times 6. Well, that's going to give us 16 minus 24, which is going to end up equaling a -8. And because it's negative, that means that I have no real solutions here. And if we have no real solutions, then that means that this is in as simplified form as it gets. Meaning that there is no hole, because we can't cross anything out. So if there's no hole, and we checked and there are no real solutions, we are not, that means that there's also going to be no zeros. Now, when it comes to our vertical asymptote, we're going to do the same thing we did before, take our x minus 4 equal to 0. So x is going to be 4. That's our horizontal asymptote. To find our y coordinate, we can plug 0 in. So we get 0 minus 4 times 0, 0 squared minus 4 times 0 plus 6 over 0 minus 4. And we end up getting the point 0, comma, -6/4, 6/4, which is the same as -3/2, or -1.5 there. Now, because the top is bigger than the bottom, we know we are going to have a slant asymptote here. So in order to find that slant asymptote, we are just going to divide these two polynomials. Now, because this bottom is in the form of x plus or minus a constant, we can actually use synthetic division here. So I'm going to use 4, because we want to switch our signs. 1, -4, and 6. Bring our 1 down, we get a 4, 0, 4, 10. So based on this piece right here, this tells us that we have a slant asymptote at y equals x plus 0, because this would be our x value and our 0. So y equals x. So that means as we're drawing it, we're going to have a slanted line at y equals x. Now we have a couple of extra points here that we can plug in. We're going to do it the same way we did before. So we would do 2 squared minus 4 times 2 plus 6 divided by 2 minus 4. As we plug that in and calculate it out, we get -1. For 2, if we put a 1.5, we get a -0.9. A 6, we get a 9. And a 6.5, we get an 8.9. Now, as we graph this, it's actually super important to recognize that these points here, this one here is going to be a maximum value, and this one here is going to be a minimum value. Okay, so that means that's kind of where our asymptote stops. Now, as I mentioned before, if we have a slant asymptote, we want to wait to do our domain and range until after we've graphed it, to make sure that we're pretty confident in where it goes. So as we're graphing this, we have a slant asymptote at y equals x. We also have a vertical asymptote here at 4. Okay, so we have our two asymptotes. Now, using these numbers, I can see that I have a value at, so this is 4. I have a value at 2, -1. I also have one at -1/2, -8.9. So that's our maximum value here. So this function's actually going to end up looking something like this, where this is our highest point. Then we have our other 2 points where we go to 6, 9 right here. And then we have 6.5 and 8.9. So this one's going to look kind of like this, staying within our boundaries there. Now, our domain and range. When it comes to our domain for a slant asymptote, it's going to be the same as before. So it's going to be all the real numbers, except for if we have a hole or the vertical asymptote. So in this case, except for 4. When it comes to writing the range of a slant asymptote, do you see how from right here to right here, we don't have any values in this area? When it comes to writing our range, we want to take that into account. So in this case, we're going to have all real numbers, except for the interval that goes from -0.9 all the way up to 8.9. Okay, so it's going to be all of those. Another way that we will commonly see it written is it'll say -infinity to -0.9, where 0.9 is the last point we see. Or we're going to see the values from 8.9, which is the first value we see, to infinity. Either of these methods here will work. So the set containing that interval or this, either of these will work here, but we want to make sure that we're being consistent and understanding what that means. So it goes all of the values except for the ones right in that chunk there. If they're in that chunk, then they don't get included. And that is how we can use that slant asymptote. So if you have any questions, don't hesitate to reach out, but that is how we can graph rational functions in different forms.